Hello.
Hi.
So I think today we'll change the format a little bit. So we'll do some revision using slides. So this way then you have to write the formula again, and then we'll continue talking about linear transformations. Yeah. So let's wait. Well, it's 8. Yeah, we should probably start. But we do expect more people to join, right?
Yes. They are coming, I think.
Okay, good. Do you have any questions meanwhile? Maybe about homework or anything?
Not really.
So everything was okay? So you were able to solve the homework?
Yeah, most of them are okay. And I asked TA for some questions.
Yep, great. Hi, Sophie, welcome back. Do you have any questions?
No. I have one. I'm not very clear about what rank means.
So it was already in the, well, we'll get, so it was already in the homework?
No.
Yeah, so,
yeah.
So that's coming, yeah, so
okay.
Is the, so if you have a matrix, say n by m, right, like here, right, so, and then if you have a, in this vectors, right, so you should think of a matrix as a, you can think of it as a list of columns, right? And then if only say k of them are linearly independent, then the rank is k. Yeah, so it's the maximal number of linearly independent vectors that form the matrix. So for example, if you have a matrix like this, 1, 0, 1, 0, and then 1, 1, 0, its rank is equal to 2, right? Because, well, this column and this column, they're linearly independent, but this one, you can write it as the sum of the first two. So rank of this matrix is equal to 2. But we'll come to that, yeah. It's one of the next topics. Does it explain does it answer the question? So for example, my matrix, one like this one that it has rank 3 because it has 3 linearly independent vectors. And the first matrix that I wrote has only 2, so therefore its rank is equal to 2.
So it's like the number of the pivot column?
Yes, that's the number of pivot column, yeah. That's not the way to say it. It's the number of pivot columns in the echelon form. But I believe it should not have appeared in the homework yet, right? So, because I wasn't worried that. So is the third person coming, or we should start?
Maybe there's no third person.
I believe there are 3 enrolled students in class, and Lucia told me that because of this exam that some of you guys took last week, not everybody was present. Yeah, so I was talking, so maybe I asked her, so she was a bit reluctant, but maybe you guys can say for yourself. So we can either do what we're doing right now, so we can meet every day, like Monday to Thursday, and do this lecture/discussion thing, or we can do the following. I can pre-record all the lectures, and then like for the given week, and then we'll just meet one time, like live for discussion. It will do like 2 hours full of problem solving. So some instructors do that. So we can choose. What do you think? Which format is better works for you?
That sounds great. You mentioned before. Yeah, once a week, we came once a week for discussion, and then
Yes,
we watch the recording.
this way we'll all will be more flexible. So I can just pre-record all the videos on Zoom, right? So say this week's topics will be what linear transformations, matrix operations of matrices, ranks, as you mentioned. So I'll record all the lectures, give you links to the videos, give you slides and notes, and you can work on this at your own time and your own pace. And then say on Thursday, or pick any day you like, we meet in class like this, and then we do the discussion of problems.
Yes, I agree.
You like it? Sophie, how about you? Which format you like more?
I think this format is good.
I mean
Just like
the second one.
Yeah, you record the video down and we can have one-day discussion. It's okay. Right.
So you also agree that it will be probably more efficient, yeah? Because I know, like, so in Berkeley here, so we had even like the chair of the department even advised to do that. But so still, with my students in Berkeley, I did like, you know, we met every day, but then so the attendance of the class dropped because they knew that they can watch the video. So this way, you know, I think like I had 100 students enrolled in the class, and maybe at most 20 showed up every time. So for the discussion, of course, almost everybody showed up. But for the like everyday routine lecture, it was not like this. Okay, good. So then I'll let Sonia know, and then sorry, not Sonia, Lucia, right? But is it true that you guys have American name which is assigned by an English teacher, right? So Iris and Sophia are not your Chinese names, are they? Well,
what?
No, the question was like, in China you're given American names, so to say, like English names. Do you pick the name, or it's given by someone?
It's given by my primary school teacher.
Oh, I see. And do you have to pick it, or you can? It's more or less you're not free to.
Sorry?
Did you pick Sophie, or was it assigned by the teacher?
Just science. Yeah.
Oh,
she science.
Yeah. I thought so. Iris said that she picked it by herself. Yeah. Well, I guess every school is different. Okay, great. So then I'll email Lucia and then ask her sort of so that you guys. The third person I haven't met. So there's someone with a.
Maybe today's only 2 of us because Lucia has said in the group that only 4 person come to live, but one is going to the French courses, another one, I don't know, he or she just go to the hospital today. So today maybe only 2 of us.
I see. So that person in the hospital, is he or she will be okay? Is going to continue, or you don't know? But even regardless, I think even if this is the case and you like the format with recording lectures, we should do it. So I'll tell Lucia, and we can switch to that format. Okay, great. Okay, let's get going. So, yeah. So any other questions about math? Right. So let's remind ourselves quickly what we were talking about last week. So we have matrices multiplied by vectors. Right, so here we have a matrix of sizes R, which is number of rows, by C, which is number of columns. So we're going to multiply matrix by, so this is the matrix vector multiplication and get what we see on the right-hand side. And this way, a matrix defines a map, right, between from RC to to the power little r. So it's a linear transformation, as we already know from last week. So which takes a vector x and assigns this matrix A dot x. Okay, so then we talked about when does the equation ax equals b have a solution for any b, and then sort of the answer was given in terms of the row reduced matrix, right? So we knew that when every row of A has a pivot, right? So then the sort of as we saw last time, the ax equals to b has a solution, right? And exactly when the augmented matrix has no pivots in the last column, right? So that's another way to say it. So if you didn't have if there is already pivot in every row, right? So you can think of pivots in rows and columns, then there cannot be pivot in the final column simply because, well, there's one more column. There's like extra column that you add. Right? So in terms of rows, that means that the rows are linearly independent, right? So if you say that every column of matrix A is a pivot column, right? Maybe we can let's do it again. So if we had this augmented matrix, and then sort of the last column was this vector B, right? So if every column is a pivot column like this, it kind of goes as a staircase, right? Then so it's 1, 1, 1, 1, 1, and so on, and there are zeros on top. And then the last one, so the last column on the augmented matrix is not a pivot column, and so forth. So here we have like say x xc is equal to some number bc bn. So that also means that there is no non-zero linear combination of the rows of A which is equal to 0. That's the definition of linear independence. So the fact that ax equals to b can be thought of as the condition that B is a linear combination of columns from matrix A. So here's an example. So here's a clarification. So if it was the case, then by row operation, sort of by reducing the matrix to echelon form, we'll have the row of the form like 0, 0, 0, and 1 in the augmented column will be created for the matrix of some choice. Okay. Questions so far? Okay. And then in terms of columns, we say that the columns of A span the entire space, right? So that's the again, the statement of linear independence of vectors is that the span of the vectors gives you you can construct the vector space A by doing the span of all column vectors of the matrix. And then, so sort of in this language, the solving ax equals to b means that you want to write b as a linear combination of columns. So we didn't talk about this. We didn't talk about associated functions. Let's skip that. Yeah. Okay. So right. So then, as we said before, as I said in the beginning, so remember this associated linear transformation A. It takes you R elements from RC and maps them into elements of R to the R, right? So this is a associated linear function to the matrix. That's what that's what the name is. And then solving AX equals to B means that you find a point which maps to B, right? So let's do it like this. So if this is one, RC is this one blob, and R is another one, So there's a function that maps you from here to here. So we take x, vector x in this space, and then we map it to y, to b, excuse me, to b in that space. So you need to find a vector x that is sent to vector b by this linear transformation. And now, so that means that if every point is hit by the map, then this always can be done. So in other words, if it's true for every, so if every value of x comes to, so when can you do that, right? So is when so for every point b, there's an element x in the domain of this function, right? Such that ax is equal to b. Now, so just to summarize, if A has R rows and C columns, with the following statements are equivalent. This inhomogeneous equation, right, Ax equals to B, has solutions for any B. Matrix A has a pivot in every row. The rows of A are linearly independent. And the columns of A span the vector space RR. Okay. It's just I'm going to pause for a second, let you look at those statements that will let you sink in.
How to distinguish the equation are linear independent or dependent?
Oh, you probably missed it last time. So do you remember what linear independence is? So vectors, if you have a set of vectors, say v1 through vc, right? With this set of vectors is linearly independent. What does it mean? It means that the only linear combination of these vectors, which is equal to 0, right, plus a plus ACVC. The only combination which is equal to 0, like 0 vector, is such when all coefficients are equal to 0. Right, so for example, vectors 1, 0 and 0, 1 are linearly independent in R2, right? Because to make a 0 vector out of summing these two vectors, the only way to do it is to multiply each of them by 0, right? And if it's not clear, we need to do a step back here. So we did talk about linear dependence. I believe it was one of the lectures that you were not present, but Iris, do you remember that?
Yes, I think we just talked about the linear independence at the end of the meeting.
And that was the end of last week, right? Yeah, so basically okay, let's do one more example. To say for example, vectors, 1, 2, and 2, 4, they are not linearly independent. They're linearly dependent, right? Because you can multiply this vector by -2, this vector by 1, add them together, and you'll get 0 vector.
I got it.
Yeah, so see, here they are proportional to each other. So yeah, and then so vectors like 1, 0, 0, 1, they are not linear. They're linearly independent. And sort of, if you get back to the pivot in every row, right? So it means that by row reduction, you can reduce matrix A to this form, 1, 0, 0, 0, 1, 0, 0 here, and so on. So like only once on the sort of sorry, every row is a pivot row, right? Like there's one, well, we shouldn't draw the quadratic one. Yeah, so so like there's a pivot in every row, meaning that there are no empty rows with, like, you know, if you want to solve it for every b, so like this last column is filled with elements, say b1 through bc, and then if it will happen in such a way that the last row will contain a bunch of zeros and nothing else, then there is no solution, right? So the only solution is when bc, the last component, is equal to 0. We don't want that. We want to have a solution for all values of b, right? And for this to happen, every row has to have a pivot element. So there should be one somewhere, and one in this row, and one in that row, and in all other rows. Yeah. So is this part clear about a pivot form in rows?
I'm clear.
So, good. So now let's try to explain why it's equivalent to the last one. So that columns of A span R to the R. So remind you that there are rows here. So it's the same idea, right? So if you look at, so let's look at only, you know, because when you do to the pivot form, we only have to take care of pivot columns, right? And all pivot columns will have a form, you know, 1, 0, 0, 0, 0, 1, 0, 0, and so on. So there will be R vectors such that there will be one at one of the places and only one in for that vector, and zeros everywhere else, right? So so clearly they span RR, right? Because you just these are like the, you know, the vectors. So every element, every vector in RR can be obtained by a linear combination of these two vectors. Well, we'll talk about this later. It's called the basis. It's the basis in RR. Okay. We talked about linear dependence. We talked about span. Sophie, you remember about span? It's you look at all possible linear combinations of all vectors, right? So like, if you look at all possible values of A1 through AC, so that will give you span. So this is zero, so it will be span of these vectors E1 through VC. So for example, if you go to say 3 dimensions, you have 3-dimensional space x1, x2, x3, then span of vectors I and j. Well, you know, these are the standard basis, the standard vectors, the unit coordinate vectors in 3-dimensional space. So what is span of I and j? How would you describe that thing?
It's a 3-dimensional.
Well, yeah, the space is 3-dimensional, but we only look at 2 vectors. So span of ijk will be the entire thing, entire space, but now I only take 2 vectors.
So it's gonna be a plane.
Sure. Yeah, it's the x1, x2 plane, right? Because every vector here, see this vector, is I times not some number plus j times some number. It's a linear combination of I and j. Okay. So in this example, vector I is 1, 0, 0. Vector j is 0, 1, 0. Vector k is equal to 0, 0, 1. And now let's reformulate the statement in terms of this thing, right? So now let's say you have some vector b, right? So you want to find a vector. Say vector b is just arbitrary vector in 3 dimensions. Now, what's the meaning of this system of equations? It means that, so the role of x will be the coefficients, right? So if vector b has components x1, x2, x3, then we can write this the same equation, the same statement. We can rewrite it as such as that as the matrix A multiplied by vector x is equal to b, right? Where matrix A is 1, 1, 1, and the rest is 0. Do you guys see that? So yes, well, this is probably the most direct example. So we know that every vector in 3 dimensions can be represented as a linear combination of the basis vectors I, j, and k. That's how we introduce the coordinate system. Now, this very fact we can interpret as existence of a solution of this inhomogeneous equation ax equals b for every value b. Right, and you see here that the matrix A has pivot form, the echelon form. It has 3 pivot rows, and the columns, they generate the entire space. What do you say? So we have just went over every step here.
So A here is like identity.
Yeah, A is the identity matrix. Yeah, we haven't talked about this, but yeah, so it's like it's the matrix of the identity. Actually, I'm sorry. I think I made. Oh no. Yeah. So right. So yeah. Right. So, right. Yeah. So here A is the matrix. Yes. A is the identity matrix. So because this it simply means here that it's vector I times x1, right, plus j times x2 plus k times x3. And clearly for this diagonal identity matrix, number 2, 3, and 4 are satisfied. So if you take a rectangular matrix, right, so then it will be more interesting. So there I just have to check that we have what it says, that every pivot row, there's a pivot in every row, and then that's equivalent to say that all rows are linearly independent. And because one stays at some position where the rest elements in the column are 0. Okay.
Okay. I think the theory is sometimes hard for us to understand. We may want to know how to use it, or just see some.
There are examples in the homework, right? So this already should have been in the homework.
Okay.
So yeah, so let's see if we have another example here. So so I just gave you the example with the vector in 3-dimensional space, right?
Okay.
Yeah. Okay, so let me know if it's still unclear, then we can come back to that. Say, yes, okay, so if you agree with this recording thing, so this is basically collect all the questions, so like Thursday will be a complete sort of problem-solving Q&A session, right?
Yes.
Yeah, sure. No, but yes, well, today we'll just continue as we did before, and then yes, we'll switch starting from tomorrow. So I'll start recording tomorrow. Okay. Anyway, so yes, so and then yeah, okay. So good. So here's that.
Okay.
Oh yeah, there's one more. The function corresponding to A, this linear function, hits all of RR, right? So it's, in other words, the image of this function is the entire codomain. It's like is the entire R-dimensional space. Well, zero solution, that was the uniform equation in our previous terminology. Sorry, homogeneous equation. So homogeneous equation has always zero solution, and just multiply everything by zero, then it's equal to zero. And of course, inhomogeneous equations do not, right? You have 0 equals b, it's only true when b equals 0. So it may not have any solutions. And then the fact that a times x equals 0 have the only 0 solution. So let's rephrase that, right? So that every column of A has a pivot. That the coefficients, free parameters, they're all equal to 0. So if you say that ax equals to 0, so ax, you can write it as a1 x1 plus a2 x2 plus and so on plus x, let's say c or ac. Oh, I put in back, sorry, I put in arrows in one place. No, I was right. Oh, sorry, it's been a long day here. Times xc. So that's, in other words, it's a linear combination of vectors e1 through ac, where these vectors are column vectors of the matrix A. And so you can think of A matrix as a list of these column vectors, right? So A1 through AC. Yeah. So if we require that this is equal to 0, and the fact that this equation has only the 0 solution means that vectors A1 through AC are linearly independent, right? So in other words, there's only a trivial linear combination. So in other words, if all x's are 0, which makes that 0. Yeah. So there's 0, there's at most one solution. Yeah, so if there's one solution, there are no others. Yes, columns are linearly independent. So yeah, this is just, it repeats what I just said. So that's how you can write it. And if this equation has only the 0 solution, that means that the only way of doing this is to have all coefficients to be 0, which is the definition of linear dependence. Well, I hope this should be clear. So remember, we talked about last week that how to find the solution of an inhomogeneous equation from homogeneous equation. So you need to find a solution, some solution of homogeneous equation first. In this case, it can be either trivial solution. So this 0 solution is called also sometimes trivial solution. It may have trivial solution, or it may have some non-trivial solution if columns are not linearly independent. And then just add to that solution any solution of the inhomogeneous equation. Okay. And yet the same condition in terms of rows is when the rows span the space. And yeah, let's see. Do you think it's the So do you see that this is the same condition, that this is a zero? It only has zero solution if rows span the vector space RR. And so we have say the rectangular matrix, right? If you reduce it to the echelon form, you will have once every row will have a pivot form, right? And then they will be this is RR. They'll span the entire space. Okay. So okay, we just basically said that. And finally, in terms of this associated linear function, when the function determined by the matrix A is 1-to-1, right? So in other words, what does it mean that 0 is the only solution? So let's talk about this. If you have so this is one space, this is another, and there's a map A from one space to the other. So we know that 0 vector here, when x is equal to 0, 0 goes to 0 by any linear operation like that. Now, if this is the only point from the left, right? So this is RC, this is RR. If this is the only point, if 0 is the only vector in RC such that A times this vector is equal to 0, it means that the matrix function is 1-to-1. So, which means that the pre-image of this point, let's say there's some point B here, right? It will go to some other point here, some vector A, such that A epsilon vector A is equal to B, and we know for sure that A is not equal to 0. So in other words, the map will be 1-to-1 for every value for every vector A on the left. You'll find a single vector B on the right, and vice versa. So yet another way to say it is the following: that if this equation doesn't have only there's some other solution other than 0, then what happens is this: this is your domain of function A. It will map it to the codomain, and then there will be some subset here which will go completely to 0. So that subset contains 0, of course, right? But if the first line of the slide is not true, so if there are other solutions other than 0, then they'll go here. And in this case, the map is not 1-to-1, right? Because all these points, all these vectors which live inside this blob will go to 0. It's like, if you have a function of one variable, it means that your graph of this function looks like this, right? So it fails the vertical test, right? So for one value of x, there's more than one value of y. Does this sound familiar? Good. It's like I do recommend you to sort of look through the slides and notes again when you do the homework, and just so it will take some time for these concepts to sink in, but after some time they will become very natural. So in other words, if this associated function or linear transformation A is 1-to-1, it means, and it goes both directions. It means that the only element in the domain that is mapped to 0 under this function is 0. So there are no non-trivial pre-images of 0. Let me give you an example when this is not the case, right? So we'll look at classification of, we'll look at a bunch of examples of linear transformations. Let's take the following matrix. A is equal to 1, 1, 0. As a map from, so of course, like Euclidean three-dimensional space is a very nice example. As a map from R3 to R3. So can you describe, we'll take a minute to think. So can you describe what does this linear operation do? So take a vector x, act it with some vector x of your choice, and then see where this vector lands. Maybe you know even the name for this transformation.
Sorry, Peter, can you repeat again the question?
Do you see the matrix A that I just drew? So it's
Yes.
1, 0, 0, 0, 1, 0, and the last row is 0.
Yeah.
And this is the linear function from three-dimensional Euclidean space to itself, right? From R3 to R3. Okay. Can you describe what this function is doing in terms of, well, three-dimensional space? So let's see, act with A on some vector x, right? So pick a vector x, it's like, and see what is it equal to. So yeah, go ahead.
Is A here an augmented matrix or just a
No.
matrix?
This is the function. It's this linear transformation. It's the matrix of this linear transformation. We don't need augmented because the right-hand side is 0 anyway. So we just studying this transformation.
So it's gonna be a plane.
Yep, that's right. Which plane? Which of
a plane through XY?
Yep, that's right. So the reason for it is because so let's say we act on a vector x, meaning that we have, if x has components x1, x2, x3, then the image will be x1, x2, 0. So what it's doing, it's taking, so let's try to draw it. That's the x1, x2 plane, right? And then say we started with a vector here, some vector A. So what it does, it projects this vector down to the x1, x2 plane, right? Because it simply, the third component is always 0. So this linear transformation, it forgets about the x3 component. So no matter what it was, right? So the vector might go like this, like that. After the application of this map, the image will belong to the x1, x2 plane. So this transformation is called projection, because that's what it does. Like it projects things down onto x1, x2 plane. Okay. So Iris, do you see that? Is it clear? Do you see why this is a projection?
So why does the line have a direction to the x3? Because they're only including x1 and x2.
Yeah, so good. So that's the next question. So what happens with the line that is parallel to x3? Not parallel, but coincides with x3. So let's take a vector, with components 0, 0, 1. What's the image of that vector?
It's a line just through the x3.
Well, let's check. So x3, but x3 goes to 0. So if you apply multiply matrix A by vector 0, 0, 1, what are you going to get?
Oh, x3, 0, 0, 1.
Let's just, so you know how to multiply matrix by vector, right? Let's erase the stuff. So multiply matrix 1, 0, 0, 0, 1, 0, 0, 0, 0, multiplied by vector 0, 0, and let's put, you know, any value A. Which vector is that? What are the components of this vector?
Zero, zero, zero.
Yep, exactly. So no matter what A is, right? Which means that every vector like this, will go to 0, to just to 1 point here. So in other words, the 0, the 0 vector is not the only solution of this equation. So if you try to solve Ax equal to 0 equation where A is given by this matrix, then 0 vector is not the only solution, or rather all vectors of this form are solutions. And geometrically what it does, it takes the entire x3 line, x3 axis, and projects it down to a point, to the origin. And of course, it means that this map is not one-to-one, right? So point 0 here has infinitely many pre-images. So every value of A, every vector that is parallel to x3 axis will go to 0. Okay? I'm not saying anything, okay, maybe it's confusing. So I'm not saying anything complicated. So it's perhaps just, if you just write the formula, it looks very straightforward, right? So you know how to multiply matrix by vector. But let's try to understand what this means geometrically, right? And understand, because that's what linear algebra is about, right? It's like, in terms of calculations, it's just a bunch of matrices, and you can teach computer to do it. In fact, I showed you last week a lot of calculations with Mathematica. It's very easy to teach computer to do these calculations. So once you understand the mechanism, it's done. It's like it's the, you know, it's just the technology of the machine. But it's interesting to understand what's going on geometrically. Right? So this example sort of is very sort of nice because it allows you to understand exactly what's going on here. So remember what we talked before, like that the in terms of rows, when the rows span, right? So rows should span R3. Well, here clearly they do not span R3, right? Because these rows, they only span the two-dimensional subspace of R3, right? This is just 0. And then the matrix also in terms of pivots, right? There are only 2 pivot rows, and there should be 3. So in this example, that we had before in the previous slide, right? So when the matrix A was 1, 1, 1, right? The 1, 1, 1 on the diagonal. So there, that matrix was 1-to-1 map between the image and the domain and codomain. This guy here, the projection matrix, is not. And the subspace of R3, which is mapped to 0, consists of the entire line, the entire x3 line. And so this line is parameterized by this column vector, and it's sent directly to 0. Okay. Please ask questions. I think it's better to get this result right away. It's not that complicated after all. Yes, we can move forward. Okay, good. That's good. Okay, we talked about that. Yeah, so in other words, if 2 points are sent to the same point, then you can write it as a of x minus y is equal to 0. And if 0 is the only solution, then you have x equals y. Yeah. So the only way 2 points can be sent to the same point is if they were the same point to begin with. That's another way to say it. Okay, so again, there's some a list of equivalent claims. If A has R rows and C columns, then the following claims are equivalent. AX has only 0 solution. AX equals 0 has only 0 solution. The matrix has pivot in every column. Columns are linearly independent. Rows span all of RC. And the function corresponding to A carries distinct points to distinct points. So it's a one-to-one correspondence. Okay. So this is just a summary here for the homogeneous equation and then for the inhomogeneous equation. For the inhomogeneous equation, AX equals B has solutions for every B. If, right, so pivot is in every row. Rows are linearly independent, and then columns span the whole thing. And then with the homogeneous equation, it's sort of it's a bit it's in a sense it's the complementary, right? So it's the pivot is the column, columns are independent, and rows span RC. Okay, and so it's a useful summary here. Now, if matrix A is square, which will be well a big chunk of our calculations, then there's a pivot in every row. If and only if there's a pivot in every column, well, simply because the number is the same, right? So kind of these are equivalent. Okay. So a quick recap for span, right? So we say that if a collection of vectors in Rn spans, if every vector in Rn can be written as a linear combinations of vectors from this collection, right? The collection is linearly independent if whenever this is equal to 0, if it means that all AI is 0, all AI is 0. So we are dealing with a trivial linear combination. A collection consists of single vectors linearly independent because you can just multiply it by 0. That's the only thing you can do. And then 2 vectors are linearly dependent as long as one is not a scalar multiple of another. And so all vectors, they look like this. They're linearly independent no matter what they are. Okay, so now let's look at some examples of linear transformations. Are there any questions before that?
No.
So one is called shear, right? So it's you have the, well, it happens say in on Earth, right, with different tectonic plates, kind of this oceanic crust and land crust, and they sort of they shear one stick and the other. So here's what's going on in here's how you can write it. There's a the bigger the value of y, the longer is the displacement in x. Then there's a reflection. We'll write the formula soon. So like then there's reflection. So you take it's also called mirror symmetry. So there are 2 examples with horizontal reflection and vertical reflection, but of course it can work relative through any axis. Rotation. Well, the name speaks for itself. Right? So let's see what's going on geometrically. We want to understand this in terms of matrices. right? So linear transformations take lines to lines, as we know that, we'll define it in such a way that it will also preserve the origin, right? So, well, I mean, we know what the line is. Basically, we know how to parameterize lines in terms of parametric coordinates. So, but still, nevertheless, let's define it algebraically, right? So here's the definition. A linear transformation is a function from RC to RR, right? So we use the same notation because we'll use matrices to denote that, such that T of A times V plus B times W is equal to A times T of V plus B times T of W. Here, so both V and W, they belong to this set RC, right? So this is a linear combination, and then A and B are real, just with real coefficients. So in other words, a transformation is linear if after applying it, so if it maps linear combination of vectors into the linear combination of images of those vectors. Okay. So now let's yes. So this is the definition. We'll get to some examples momentarily. So if you have two sets x and y, right? So we have the function, it gives some element f of x of y for every element of x. So this is just, it works for every function. It doesn't have to be linear. Now we define domain of the function. X is called domain of the function, y is called the codomain. And the range of the subset of y, the range is the is a subset of y where all elements from x are sent to. And then finally, the function is said to be one-to-one if no two elements of x map to the same element of y, and is said to be onto if every element of y is hit. And in other words, the range and codomain are equal. So first, have you seen this definition before? Are these words domain, codomain, range, are they new to you, or you know what this is? If they're new, I want to explain more with the picture.
I know them.
You know them. How about Sophie?
Yeah, I know it.
Right. Yes, sounds good. Yeah. Well, I mean, in this case, maybe I can give you a little bit of more. So if this is x and y, right, and then there's a function f, right? So then what we said before, say there's a subset of x such that, let's call this well, so there's a subset U. U is a subset of x such that for every x inside U, f of x is equal to 0. Do you know how this subset is called? So it's all elements of x which are sent to 0 in y. So U in this case is called the kernel. So it's the kernel and kernel of f, and you know what it is. So U is ker of f. In our example with the projection map, the kernel of this image consists of the entire x3 coordinate axis. So again, so kernel means that all elements, it's a subset of domain which is sent to 0 in the codomain. So for example, if your function, so just a quick question, if you understand what the definition, say the map f, it's unrelated example. It takes space of functions, differentiable functions to space of differentiable functions, by applying derivative to the function. So if you have a function of f of x, which is differentiable, it maps it to the derivative of x. So what is the kernel of this map? It means that we need to look at all functions whose derivative is equal to 0. What are those functions?
The inverse of fx.
Inverse of, you know calculus, right? You know how to calculate derivatives of a function of one variable, right? So the derivative of which function is equal to 0, like everywhere.
Just let the function be 0 is okay.
That is true, but there are others, right? So 0, remember, 0 is always sent to 0 by a linear map. And we know the derivative is a linear transformation, right? Because it sends you sum of functions to sum of the derivatives. What are other functions which are non-zero, identically non-zero, and yet their derivative is equal to 0? So these are functions on, on the segment 0, 1. Closed segment, right? These are constants, right? Every derivative of a constant is 0. You know this, right? So if you have a constant, its derivative is equal to 0 for any constant c. Did you know that? Right, so you have, for example, derivative of function x is 1, right? Derivative of function x squared is what?
One.
X squared? No, but did you study derivatives in calculus or not? You know what the derivative is, right? So you have a function, you can define its derivative as a limit of certain difference of certain fraction, right? So in particular, if you have a function which is constant, like this, then its derivative is equal to 0. So like it shows you how the, let's say if you graph it, so you have a function, like this, right? And then the meaning of the derivative is the slope of the tangent line to every point, right? So derivative of this point is given by the tangent of this angle, which shows you the essentially it shows you how steep the function changes. And if the function is constant, well, then the derivative is 0. So the kernel of this function will be all constants, all real constants, including the one which is equal to 0. Anyhow, so if you still haven't taken this calculus yet, what can postpone? Okay. Any question? Any other questions here? Yeah. So it's 1-to-1 if two elements. So what may happen, and then maybe one more. So what is range. So x can go into, say, f of x, right? And we say that the function is onto if f of x coincides with y. So if f maps from x to y, and then the image of the entire set f of x coincides with codomain, then it's an onto map. And then of course there's a one-to-one and onto map. So that's, it's every two elements are sent to the same one, and then the image of f is the entire codomain. Okay, good. I'm glad that we. Yes, question?
Sorry, Peter, we have no idea about what the kernel means in this picture.
Good, so let's get back to that example with, let me give you some more space. With the derivative or where? Or just
kernel.
Yeah,
kernel?
But like, you don't understand kernel like in general? Well, okay, let me give you an example, right? So say you have, let's get back to our example with projections. I hope we understood that one. So we take the matrix A, which is 1, 0, 0, 0, 1, 0, like this one. So we're looking at values x, vectors x inside R3, such that ax is equal to 0. So that's the definition of the kernel. So kernel of A is the set of all x such that this is true. So it's a subset of the domain whose image is equal to 0. So in this example, kernel of this matrix is span of vector 0, 0, 1.
So it's like the origin of a subset?
So origin 0 is always in the kernel, right? Because if it's a linear map, it takes 0 and maps it to 0. Now, for some maps, that's all there is. There are no other elements which are sent to 0.
So what's the relationship between the kernel and the subset?
No, kernel is a subset, right? So subset is just a notion from set theory. You have a set, you have subset, and just some elements which are inside it. So, so whenever if you have a function a from, let's say x to y, right? So you're looking at elements in x, subset of elements in x, for which this is true. So kernel, it depends on two pieces of data. The x, the set, the domain, and the function.
Okay.
So it's the kernel of the function which acts from given domain.
So like this kernel is like a space in a subset which
it's a vector subspace. Yes.
There is a vector subspace that lets the ax equals 0.
Yeah.
So it's so the subset the kernel may include it in a subset.
Yes. So kernel, I mean, everything is a subset of something, right? So kernel is a subset of x, such that for every element little x from this subset, right? A times x is equal to 0. So in other words, if you take this matrix, switch color, right, and you multiply it by this vector 0, 0, 1, or 0, 0, 1 multiplied by any constant, right? Then you will get 0. Okay, so just let's rephrase this. So we'll give you another example. So you have matrix B, which looks like this: 1, 0, 0, 0, 0, 0, 0, 0, 0. And again, B is a function from R3 to R3. Okay?
Can you just draw the picture of the vector space and show where's the kernel
In the previous example?
for the picture?
Yes.
And
For what? For this matrix A?
both okay.
Okay, so let's do it. Then we'll get back to B in a second. By picture, you mean the three-dimensional space, or this with blobs, with subsets?
Three-dimensional space is okay.
Yeah, okay. So yeah, look at that. So we have and so there's the three-dimensional space. Now claim that all points which lie here on the x3 axis, all vectors whose components are 0, 0, and a, where a is any real number, right? So this is the kernel of map A. So in this case, kernel of A is span of this vector, right? Because well, what are these vectors? These are vectors like this, which have you know, which go along the vertical axis.
Okay, we got it.
Good, yeah. Good. Okay, so if you got it, what is the kernel of the following operator, of the following matrix? B equals 1, 0, 0, 0, 0, 0, 0, 0, 0. What's kernel B? Yeah, I'll be back in a minute. Yeah, so think about that. Yeah, I can see the correct answer. Yep, so 0, it will be, well, I mean, yes.
So, so curl of B means that let's the curl of B times B and let the final answer to be 0. It's okay. So there's many solutions to this curl B.
Yeah, there are many solutions, but it's a vector, it's a subspace. So for A, the subspace was, well, we haven't defined dimension yet, but yeah, because it will be this line, it's this one line. And for B, it will be the plane, right? Which plane? So every vector in a certain plane will be projected to 0. Which plane is that? So I'm going to change the picture. So Sophie is writing 0, 1, 1. So I think what you meant is the following. What you meant is that the, what's the response? Some stuff here. So the right way to say, right thing to say will be to say that this is equal to span of vectors 0, 1, 0 and 0, 0, 1. Right? You said 0, 1, 1, but that's only one of the examples. So indeed, it's true that vector 0, 1, 1 is in the kernel, but there are others. For example, vector with components 0, A, B for every value of A and B. So
the plane is through the A and B.
Yeah. So and it's a YZ plane, right? It's a plane that is orthogonal to the x-axis. And so every vector, this is x1, x is x2, x3. So that the entire plane here on the back lives in the kernel. So in other words, if you have a vector in that plane, any vector, no matter where it goes, its image, right, after we act with function b on that vector, will get 0. So it's another example of a projection operator. Well, I hope it became a bit clearer. So indeed, if you multiply matrix B by this vector, you'll get 0. You'll get 0 vector, no matter what values of A and B are, right? Yeah. So think also kernel is not just 1 or 2 vectors. It's a space. It's a subspace. A linear output will always have. So it's either just 0 itself, in which case the map is 1 to 1, or it's some infinite subspace which has infinitely many vectors.
So the word curl base like give you a span.
Yeah. So typically kernel B is a span.
Mm-hmm.
Okay, great. No, I'm glad that so I mean, we'll talk about kernels are scheduled to be a bit later in the class, but it's good that we already started thinking about them. Okay, how are we doing on time? No. Yeah, let's yeah, we don't have to rush. It's better to explain things more carefully. Yeah, we talked about those. I'm just giving back the builds. Okay. Right. Yeah, and then sort of just the refinement of the previous slide with the linear dependencies, right? So, yeah, I think we can just skip that. Yeah, we already talked about it. Now, we talked about linear functions, which I just know can be represented as a matrix acting on a vector column, but there may also be nonlinear functions. So say we take, you know, function like this, right? So if you sit in the room, or wherever you are, you make every point to take every point and assign a temperature of air at around that point, right? So you maybe took some physics classes, you know what roughly temperature is. You can define a function. So clearly, this is a non-linear function, right? So there is no reason why temperature should change linearly as you go from one corner of the room to another. So the domain of this function is the room, the codomain is R, and the range is, you know, depending where you live, between say 60 and 110 Fahrenheit. Yeah, I'm not sure where you are in China right now, but maybe it's also, I think it's just most likely it's hot at your place. Clearly, it's not one-to-one function, right? So many points in the room may have the same temperature all over again. But the sort of, what is the geometric reason why this is not a one-to-one function? Well, we live in three-dimensional space, right? So our room is three-dimensional. So there's no way we can, you know, there will be a one-to-one map from R3 to R, or rather it's some, you know, some, our room is not R3, it's not infinite, but it's a subset of R3. So it's never one-to-one. It's also not onto, right? Because you cannot get any temperature, you cannot go above some value. Okay, so here's the, I think we should finish with examples of linear transformations in this, at least in this chapter. So yeah, so here RC is the domain, RR is the codomain. And yeah, so what we're going to do, we'll study different examples for details of the function t, right? And then we can define for ourselves. Well, we can understand what is the domain, what is codomain, what is the kernel. There's also notion. There's a kernel. There's also co-kernel. But let's talk about that. Let's talk about that later. Okay, some examples with matrices. So take this matrix 3 by 2, right? So it determines the linear transformation. It takes vector xy to vector x plus 2y, x plus 3y, x plus 4y, right? And then it's mapped from R2 to R3. And its range, right, is span of the column vectors of the matrix. Right, so it will give you a two-dimensional subspace in three-dimensional space. Because that's what it gives, right? So we already talked about that. And so here clearly columns are linearly independent, and this linear transformation is one-to-one. And so in particular, it will map you. So if xy was a sort of is a plane, and then you map this plane into three-dimensional space, so that then after applying this operation, you'll be given a two-dimensional plane inside R3, inside three-dimensional space, which of course here is one-to-one. It maps every point on one plane to every point on the other plane. But it's not onto, right? Because the columns clearly do not span R3. Because to span R3, you need to have at least 3 columns. Good. Now, so a sort of a bit trivial degenerate example. So the zero function is linear. So if it's a function that sends everything to 0, right? So you multiply, yeah, you just take, if you multiply everything by 0, and this will be equal to 0, so it's a linear function. Right. Now, of course, every matrix of this form is a linear transformation. But example of a nonlinear, so we had one example of nonlinear function, which is the temperature in the room. Another example, which is not linear, is quadratic, right? So if you take f of x equals to x squared, you can check that f of 1 plus 1 is equal to 1 plus 1 squared, which is equal to 4. And that's not equal to sum of squares of ones, right? So, yeah. so linear functions is a very special subset of functions, right? So in terms of polynomial functions, these are constants and linear functions and the terms that are proportional to x. Of course, functions like exponential, logarithm are also nonlinear, right? Because this equation, this property is not satisfied for them. Okay, how about this? Is it linear transformation? Oh yeah, I see the message, right? So, but it sends everything to 0. How about this one? It's a transformation that sends every vector to value 2. Well, let's check, right? So if we have, so Iris thinks yes. Sophie, what do you think?
Yes.
Well, can we check why? We should check the only property that we need to check is that if f of x plus y is equal to f of x plus f of y. So fx equal to 2 for every x. Do you want to reconsider? No, why not? This is 2, this is 2, this is 2, right? Ain't gonna work. Yeah, so it's a 0, in sense it's like the image does not contain 0, right? 2 is not equal to 0, which is bad, right? And in particular, this linear property is not satisfied. Okay. This one, we're going to pass the, is it clear right now?
Clear.
Good. This is, well, yeah, so we know that this is linear, so can you write the matrix for this transformation? What will be the components of the matrix?
1, 2, 1, 3.
I think 3, 1, right? I swapped to other. The second term is 3x plus y, so it will be 1, 2, 3, 1. Right?
Yeah.
Okay. This one?
No.
Right, it's a quadratic function, right? It's a quadratic function of variables. This one.
No. Yes.
Of course, it's an identity, right? It's just the okay, good. And now let's talk about something more interesting. How much time? Oh, we still have like 20 minutes. That might be. Rotation. Let's find the matrix for rotation. So let's say, well, clearly here, so it takes if you have vector A and vector B, you add them together, you have A plus B, and of course after you do the rotation, it would still be the case, right? Because what you're doing, you're taking this parallelogram and you're just rotating it by some angle. And so therefore, you don't change in distances between those points in any direction. You're just taking it and sort of and rotating it. So therefore, rotation is a linear transformation. Yeah, that's how it goes. Yeah, so it preserves the rule of adding vectors and adding vectors with any multiple coefficients. Reflection is also a linear transformation, right? So here, the sum of the rotated vectors is rotation of the sum of the reflected vectors is also the sum, right? So you have you pretty much you do reflection of every vector, right? Relative to in this case this axis, right? Since you do it for every vector, you can check that the even see like the way I do it here, I just did the mirror reflection of the entire picture using my computer. So yeah, a reflection is also mirrored transformation. It preserves linear transformation, preserves the rule of hidden vectors. Okay. Now shear, what we had before. So that's what we had now. And then after this, we have sort of, we shifted, we kind of squeezed the picture in horizontal direction. So you can think of it like we kept the, if you do a horizontal line, right, so that would still be within these two parallel horizontal lines, but the distance between vertical lines have changed, right? So the picture got stretched. So this distance got stretched. Right, the sum of shared vectors is the share of the sum of vectors, right? We'll write all the matrices for them, and yeah, so geometrically it preserves the rule. Rescaling is also a linear transformation. So if you multiply every vector by a constant, by the same constant, then it also preserves the sum. It preserves the addition of vectors. Okay, now let's talk about matrices. How to explicitly write down matrices for each of these transformations. So let's start with rotation. So let's consider rotation of the plane by the angle theta. So here's the picture from high school, right? So we have a unit circle, and then every component, if you mark a point on the unit circle, right, its x coordinate is the cosine of the angle, and its y coordinate is the sine of the angle. And now think of it as rotating by angle theta the entire coordinate frame. And so that's the new x and y after the rotation, right? And our task is to find new x and new y as functions of old x and y. If you want, you can call them, x prime, y prime, and this is x and y. So let's see how it goes. It takes vector 1, 0, right? It takes this vector here to this vector over there, 1, 0 to cosine theta sine theta. And it takes the vertical vector 0, 1 to this vector with coordinates minus sine theta and cosine theta. So you can write it as a matrix. Yeah, that's how it works. Right, so you can check explicitly that this matrix is on the diagonal we have cosines, and in the upper corner you have negative sine theta, in the lower corner you have sine theta. Yeah. This is the rotation matrix. It works for every vector in R2 with any components. Okay. And of course, you can rotate by negative angle, then you just change theta to minus theta. So if you rotate in the clockwise direction as opposed to counterclockwise direction. Are these the same linear transformation? Yeah, of course. I mean, well, we can check it. Okay. So let's see. I think it's the end of the. Oh, just the classification of all, right? So I just need to scale down. So shall we do it now? We have time for all of those. And we can talk about shear and reflection. Oops. I think it was fire alarm in my house. Hold on. If it beeps again, I need to. One sec. Was it the fire alarm? Oh. I'm weird. Absolutely fine. Okay. Well, I hope nothing is on fire. Okay, so I was planning to talk. Okay, so let's instead talk about the. Okay, I think we can do it as an exercise. Let's find the matrix of reflection. Yeah, so let's get back to. Let's talk about shear and reflection. Okay, and we can probably end on this today. Otherwise, probably will be too much theory. Okay. So, oops, sorry. Yeah, so let's get back to this. Yeah, so this is the matrix of rotation. Now let's do rescaling. So which transformation does the rescaling? So say we have. So we need to write down the matrix, which would send a vector A to lambda A, vector B to lambda B for every vector A and B. And so, what kind of matrix would do that?
So it's like a combination rules.
So we need to have, say vector A has components A1, A2, and after application of this operation, it should have components lambda A1, lambda A2, where lambda is some coefficient. But what kind of matrix should it be?
Lambda 0, 0, lambda.
Yeah, sure.
I
Yes, that's right. So yeah, if it's true for every vector, it will be true for AB. So this is rescaling. That's the matrix for rescaling, or it just the. So clearly, there's a special matrix here, 1, 1, 0, 0, which you can denote it as matrix 1, and this is the so-called identity matrix. Right? And identity matrix does nothing, right? So it's an identity transformation. It takes X and maps it to X, right? It takes X, 1 times X is equal to X. So here 1 is a matrix. I know some textbooks use simple I or E. I'm just going to write 1, and from the context it will be clear whether this 1 is a matrix or just a number. So then for the matrix for rescaling, you can call it R lambda. So that it's a linear transformation that does this rescaling by lambda. So you can write it as lambda multiplied by 1. So lambda multiplied by the identity matrix. Yeah. So this is rescaling. Okay. How about shear? Maybe we should let's do reflection first. It might be a bit easier. So say, let's write a reflection relative to vertical axis, relative to the x2 axis. Right, so it should do what? If they say vector A had components A1, A2, before the reflection, right, it will have components. So what happens here? The x2 projection stays, but x1 projection switches sign, right? So here A was pointed, it has a positive x1 projection, and here A has a negative x projection. So well, again, R. I should have called this, should call it by different name. Let's call it S. So S relative to x2 acting on A1, A2 should be equal to negative A1, A2. So what's x2 should be, what is the matrix then? What are the components? Which matrix does this transformation?
negative lambda 0 lambda.
Well, there's no lambda. Lambda here is 1. Yes, but okay. So so if so here it's just 1, right? So lambda is equal to 1. But on top of this, you can also do the rescaling. So if you do what you said, then you would not only reflect relative to x2 axis, but you also stretch it, rescale by lambda. Yes, that is correct. And see which matrix will be a reflection relative to x1. If you find the mirror symmetry, mirror reflection relative to the x1 axis.
What is x1?
Oh, it's not on the picture, but like it's hypothetically you had a different problem. So you have R2, right, which has to coordinate the two axes. So in the picture, we have the reflection about the vertical axis, right? What would the matrix reflection be about the horizontal axis? So it would look like, well, we have space here. It would look like this. Right? Like that. So this transformation, we call it Sx1. This transformation we call Sx2.
So it's negative 1, 0, 0, negative 1.
Why the first one? The first one is -1. So here, look at this vectors B. Look at the red vector B. Its x1 component is preserved. What's changed is its x2 component. So nothing should happen with x1 component. Right. So that's the right. So therefore, right. So that's the image of the vector, and the matrix therefore would look like this: right? 1, 0, 0, -1. Do you agree?
Yes, we got it.
Good. Okay, but since you said it, what this matrix will do? Let's call it Sx1 and x2. What kind of symmetry is that?
Is the symmetry about the origin?
Yep, that's right. That's the center symmetry. Yep. There we go. Okay, so have to run for the next class. There is 4 minutes. Well, now let's do the shear. So we need to stretch the picture in one of the directions. How do you think we should do it? So
Times and constant.
Yeah, where should we put the constant? So if this matrix of this operation A is a 2x2 matrix, what would it look like? You need to put, yes, there's a parameter by how much you stretch it. So where should we put this parameter?
Before the matrix.
That will be the scale. So see, it should act differently in x direction than in y direction. So if you put it before the matrix, it just blows up everything or contracts it. You need to
so before the vector.
So
before x.
You want to write the method. Want to say that ax is equal to y, and then say x. So see what happened here. So if b, what changed? So the vertical component of b did not change, but the horizontal component of b changed, right? So if you have vector x1, x2, then it gets shifted to, so x2 did not change, but x1 changed by some factor. There's some let's say it's x1 plus some alpha. Oh yeah. And this alpha actually depends on x2, right? Because you see, the longer the vector, the bigger the change. So I would say that it will go like this. So the matrix is 1, alpha, 0, 1. It's not symmetric, so there's an alpha in the upper right corner. So you can. The reason why it's called shear, because remember the first picture with from the geology book, right? So you have the vectors. The higher you go, the longer is the vector. So here the vector is longer than here, longer than there. So like the growth of this vector is linear. Okay?
Yes.
And if you go to the negative direction, it would flip ordered, right? So if it's negative, then it would go in the same negative direction. Okay, great. I think, yeah, we had a lot of fun today. So what do you think? So this slides format with annotation, do you prefer this to what was before, or when I did notes, that was better? I can use the combination of both. So I think I'll just pre-record the remaining lectures for the second week, and then we'll talk on Thursday. Sounds good?
Yes.
Great, yeah, sure. Yeah, great, so I'll send an email to Lucia and then I'll CC you as well. So I'll just forward you as well. Great, so then see you on Thursday then, yeah. So let me know if you have any questions with homework, you can send it to the TA or to myself. And then, yeah, but make sure you prepare the questions on Thursday. So we have, you know, sort of, you have your, we should start with your questions.
So all the record will send it at one time, or you just separately send it to us?
Sorry, repeat the question.
I mean the record, the video record, you will send us together for one day, or just separately send to us?
Well, I'll start recording them tomorrow, and as soon as I'll get them done, I'll send it to you right away. So, hopefully you'll get all the recordings either tomorrow or on Wednesday, but I'll try to do them tomorrow.
So we will get all the record for this week before Thursday?
Absolutely, no, that's for sure. That's for sure. Yeah. So you have time to work on that. Yeah.
Okay.
And then so the plan is for the next week, I'll have more time. So over the weekend, or like the second half of the week, I'll record, you know, all lectures for the entire next week, so we'll have time to prepare. Yeah, sounds great. Great. Let's see you later then. Bye.
Bye.